Hello, today we will be learning about gas densities. We will be doing an experiment to see how heavier gases react with the lighter air around us. Here are the materials needed for our first experiment. Vinegar and baking soda creates a reaction which produces CO2, water, and sodium acetate. I found that 1 tablespoon of baking soda is equal to 1.12 grams. I was able to determine that this is equal to 0.0133 moles. There is a 1-to-1 ratio between baking soda and CO2. So for every tablespoon of baking soda yields 0.329 liters of CO2, which I determined from the equation I derived earlier. Using 1 tablespoon should produce about 0.6 grams of CO2. So I tried collecting the CO2 in a beaker. The beaker should have some reading. If not 0.06, it should have at least something. So the last experiment failed to collect any of the CO2. So I tried again, using balloons instead to collect the CO2, as this way the CO2 would not have a chance to escape. I decided to use 10 tablespoons instead of the previous 1 tablespoon to increase the yield of CO2 to 3.2 liters instead of the previous 0.32 liters, so there would be a much more noticeable size of the balloon. In order to account for this increase in baking soda, I also needed to add a good amount more of vinegar. In order to fill the balloon up with CO2, I would first need to fill the balloon with baking soda, as to drop the baking soda into the Erlenmeyer flask once I'm ready to fill the balloon up. To make sure I got all of the baking soda into the balloon, I used a funnel to dump as much as I could in, and then I used a mixing rod to shove it all through the funnel. The reaction between baking soda and vinegar is very quick, so I will slow the video down so you can see what really happens. I measured the initial mass of both balloons to determine how much weight both gained from the addition of gases. Both balloons came out to be 3.24 grams. I then filled up a second balloon full of air and made sure that both had equal volumes. When I weighed both balloons, the air balloon weighed a total of 3.4 grams, and the CO2 balloon weighed a total of 5.52 grams, a difference of about 2 grams. So the CO2 balloon was obviously much more dense than the air balloon. I then experimented to see how the density of the balloons would affect them falling through the fluid of air. I did 3 trials, and in each trial the blue CO2 balloon was noticeably faster at falling through air than the air balloon was. But this wasn't enough. I wanted to see if the CO2 could extinguish a flame of a candle, but I had no candles at my disposal, so I used a match. To do this, I first had to fill up a container with CO2. To do this, I simply submerged a bottle full of water in a tub full of water, and then released all the CO2 from the balloon into the bottle full of water. So then the bottle full of water was full of CO2. I ran into a little problem with the CO2 not completely filling the water bottle, as you will see in the next demonstration. Okay, turn it over. And then I'm just going to finish it up. Hey. Right. I initially thought that I had collected no CO2, as the CO2 most likely had poured out, but I believe that me pouring in the balloon at the last second put a little bit of CO2, which you can see in the next clip. Many of you may be thinking, wait, doesn't everything fall at the same speed, 9.8 meters a second squared? And you'd be right, if we weren't talking about the movement of fluids. So here's what's actually going on. The density of an object is determined by dividing its mass by its volume. Since we kept volume constant in this experiment, the only variable is mass when considering density. Using Archimedes' principal equation, we can find the buoyant force of the balloons. Since the balloon is completely submerged in air, and since volume is equal to mass divided by the density of the object, we can express the buoyancy force as the mass times the acceleration of gravity times the inverse of the specific gravity, which is the density of the fluid divided by the density of the object. Since the density of carbon dioxide is about 1.98 kilograms per cubic meter, and the density of air is about 1.27 kilograms per cubic meter, we can calculate that the specific gravity is about 0.657. From our newly derived equation, we can see that the buoyancy force of carbon dioxide in air is a function of the mass of the balloon times the constant 6.4386 meters per second squared. But what is buoyancy force? We use buoyancy force to determine the net force an object undergoes while submerged in a fluid. If you plugged in the mass of the CO2 balloon, which I used, into the previous equation, you would get 0.0355 meters a second. If you subtract this from the gravitational constant, you come out with 9.76 meters a second, which we saw in my experiment when my CO2 balloon fell significantly faster than the air balloon. This also shows how the CO2 sinks to the candle and replaces all the air with carbon dioxide, snuffing the candle out.